Hello everyone, and welcome to my talk on Mathieu Geodesics and Barycenters with path mappings. I am Florian Wetzels from the University of Kaiserslautern-Landau, and this paper was joint work with Mathieu, Pont, Julien, Tierny, and Christoph, Garth. The problem we consider here is the analysis of scalar field ensembles or scalar field time series. Examples can be shape matching ensembles, like the scalar fields defined on the 3D meshes on the left, scientific simulations, for example the 2D time series on the bottom, or other ensembles like the synthetic 2D scalar fields on the right. On ensembles, we consider the task of clustering, meaning which members behave similar or dissimilar, and summarization, so finding a representative for the whole ensemble. For time series, we consider interpolation to reconstruct time points between given time steps or temporal reduction. We want to determine keyframes, only save these keyframes to reduce size, and later reconstruct the full series by interpolation. All these tasks can be solved by either interpolating 2 or n members. For time series, we always interpolate 2 time steps. For summarization, we can use a barycenter object, and this barycenter object also enables the application of k-means clustering. We also focus on a topological approach. We apply the clustering or interpolation purely on topological abstractions. More specifically, we first have to find a suitable topological abstraction together with a distance metric defined on them. Then, we need to find a method to interpolate the abstract objects in this metric space. Going back to the title, we focus on the merge tree abstraction, and the interpolation of 2 trees yields so-called geodesics, meaning shortest paths in the given metric space, and interpolation of n trees yields barycenters, meaning the tree minimizing the overall distance to all members. Next, I will explain our approach on an example task, the summarization of an ensemble. Here you can see 4 members of a 2D scalar field ensemble with the height representing the scalar value. They all consist of 4 main peaks, while one of them has 5 smaller peaks growing out of it. They only differ in minor perturbations of the heights and positions of the peaks. First, we compute the merge tree of each member. The merge tree represents the nesting of superlevel sets, so the leaves represent local maxima, and the inner nodes represent saddle points of the scalar field. All 4 merge trees look essentially the same. They have 3, let's say, clean maxima, and 1 maximum containing the smaller peaks. The different orderings in the layouts are of course irrelevant, since merge trees are unordered objects. The resulting barycenter tree fits this intuition. It has 4 maxima with exactly 1 containing the 5 side peaks. Now let's look into some technical details. How are 2 trees of this ensemble interpolated? As the metric, we use the so-called path mapping distance. Computing this distance between the trees gives us a mapping between the edges or paths of the 2 trees. Each mapped path or edge can then be interpolated based on their length. In our case, this yields the following tree. By aligning the 2 layouts, we can see the intuitive and smooth interpolation. For simplicity, we skip details on how to interpolate n-trees. However, the core idea is to use an iterative scheme based on Lloyd's method, which heuristically minimizes the Fréchet energy, though it does not necessarily find such an optimum. In comparison to the previous approach, our method improves the quality of the interpolated tree. The established method was based on the so-called merge tree Wasserstein distance. Using this metric, we get the problem that the side peaks are duplicated, so that each of the 4 main peaks has smaller ones growing out of them. This is a misrepresentation of what's happening in the actual ensemble. To see why, we have a quick look at the mappings of the Wasserstein distance. Intuitively speaking, the Wasserstein distance can only map the 2 highest peaks onto each other, the 2 second highest peaks onto each other, and so forth. Due to the noise in the data, this prohibits correct mappings of the side peaks. Now looking at the resulting interpolation, the unmapped side peaks cause the duplication. They are both interpolated with non-existing edges, and thus reduced to half their size at the midpoint, but both are still there. In the case of the full ensemble, this causes the previously shown misrepresenting barycenter tree. Okay, so we now wrap up this talk with some quick insight into the results in the different applications. For the interpolation of time series, we get semantically more meaningful mappings and thus better quality interpolation, as you can see on the right. On the left, you can see that the Wasserstein geodesic is a worse representation of the actual data. Accordingly, in the setting of temporal reduction, we need fewer keyframes to obtain similar or even better reconstruction by interpolation. On the shape matching ensemble shown earlier, We got very consistently correct clusterings with the k-means method using the path mapping barycenter. Using Wasserstein barycenters, we obtain mismatched shapes most of the time. For example, on the left, the human cluster is mixed with the seahorse cluster. We should of course note that our improvements come at the cost of increased complexity. A more detailed discussion of limitations can be found in our paper. Furthermore, we also provide an open source implementation in TTK. Thank you.